My name is Sam Foreman. I'm a computational scientist here at the Leadership Computing Facility at Argonne National Lab. And today I'm going to be talking to you a bit about some statistical learning methods, data clustering, and sort of I guess what you might call classical machine learning types of ideas that can be implemented and carried out pretty easily and don't necessarily require the use of large GPU clusters, which is kind of nice, actually, about some of these things. So while I was preparing for this talk and trying to get materials together, I was trying to think about what parts of my work or my day-to-day life that I wish either somebody had shown me or that are just, I think, useful to know. Especially for getting things running and on our new machine Polaris, which was recently made public. So I guess I should start by saying the slides for this talk I posted them in the machine learning channel in the Slack workspace. So you guys should all be able to click the link and follow along. They're all online, so you should be able to follow along if you want. And the other thing I would say is that you guys can feel free to try getting started on these. So these first few slides are about contain instructions for submitting a job, an interactive job on Polaris, and then how to connect your local machine to a Jupyter notebook that is running from your interactive job. So you guys can feel free to work through this as I'm talking if you want. Also, I'm sure people are probably pretty beat at the end of this being the last day and everything. So yeah, I tried to make it low stakes and a bit more interactive instead of just sitting up here and lecturing everyone. So the first step for getting the Jupyter notebook that we will look at running is to log into Polaris and submit an interactive job request. So in these instructions, you'll obviously have to replace your username. And you can just request one node, since all we need is the one to connect to the Jupyter notebook. And this command here will launch one job with one rank for 1 hour. Once you're launched into that interactive job, then the next step is to clone the GitHub repo that contains all of the examples for today and navigate into the first section, the statistical learning section, which is what we're going to be talking about now. Another kind of common problem that I've seen that maybe is a bit out of scope, but is, I think, personally useful to know and helps is beneficial down the road and a good practice to get into. So a lot of times you see people, when they're in the process of development or trying out some new model, they will interactively try to work from within a Jupyter notebook. And that obviously has the benefit of being flexible, and you can kind of work things out in real time and try something, see how it works before you make a final commit. But that isn't necessarily always a best practice, because then you always have to run the code. If you're defining functions and things inside of a notebook, then you always have to go back and rerun the cells, and it's not clear when you have different versions and which it's just it can get very chaotic very quickly, and it's generally I mean I'm biased, but I think it's a better idea to extract the functions that you want to use in a notebook and put them somewhere else in a module file, so that every time you want to use any of those functions from within a notebook, they're always consistent and you know exactly where they are. And so a simple use case for this, so the example we'll be looking at today we'll eventually get to running the statistical learning Jupyter notebook. And inside this notebook, the goal is that we would like to be able to use functions that are implemented inside this common.py or this plots utils file from within the notebook. And so that isn't necessarily straightforward, especially when you have some nested directory structure with your notebooks being in a separate directory. It's not always very easy to get things imported and set up correctly. So one of the ways that you can do this specifically is to do a local editable install of this specific package, and then you can import it from within your notebooks. So the first kind of iteratively going through step by step, would be from your interactive job. First step is to load the Conda module, or load the Conda module that provides a base Conda environment, and then activate it. And so this has most of the built-in machine learning libraries that you would want to use. So it has PyTorch, TensorFlow with support for Horovod, and a lot of other supplementary packages, but it has the main PyTorch TensorFlow that should work well on our systems and saves everybody the headache from having to rebuild everything themselves. From within, once you've activated this Conda environment, you can then navigate into the statistical learning directory and create a virtual environment that is kind of built on top of the Conda environment. And this is useful because it gives you a completely, an isolated build that is local to this specific project, this specific directory. So this is done pretty straightforwardly by just Python venv. You have to make sure to include the system site packages so that it is able to locate different packages that are built into the base Conda environment. So that's kind of an important flag. Once you've created this environment, you can then just source this activation file, and it will activate it. Then once you are in that new virtual environment from within this statistical learning directory, there should be like a pyproject.toml and a setup config file that defines how to install this specific library. And that should go without problems. Also, obviously, at the end of this, if people are running into issues, we can go through it and try to debug that. But hopefully, this should be straightforward. Once you've got this virtual environment installed, the next step is to install a Jupyter kernel that can connect that Python to our Jupyter notebook. And so this basically ensures that when we launch Jupyter, we are able to specify this Python that we've just created in our virtual environment. And so the commands are listed here. I'm not going to read them out, but the main idea being that you want to make sure that this IPy kernel package is installed. Once that's installed, you can then create a kernel with whatever name you want to choose. And then you can also specify a display name that shows up in the Jupyter notebook. And once you've done that, created your kernel, the next step is to actually launch the Jupyter notebook from within your interactive job. So this is done by just Jupyter notebook and specifying a port. So this is kind of an important point that I will get back to. So if people are actually trying this now, you should not reuse this port 8899, since only one specific port number can be allocated or assigned for everybody to use. And so if I take 8899, then nobody else can have it, and you have to find a different one. I think Jupyter by default will try to sequentially loop through them and try to find a free one. But if everybody's starting from the same point, that will obviously cause problems. So you can pick any random 4-digit number, I think, and it should work fine. But you just need to make sure you're consistent and remember the number you pick. And so the next step to get this set up involves what's called port forwarding, which is maybe a bit complicated, but hopefully I made this nice, clear little diagram that helps to illustrate it. So this is you at your computer, and you would like to set up a connection to your interactive job, which is running your Jupyter notebook. So you have this from Polaris login. You have some interactive job that's running over here that is running our Jupyter notebook. And so we can connect all of these things together by using port forwarding. And so the basic idea is that you can forward this port, whichever 4-digit number you chose previously, using this command. And that will first forward the port to the Polaris login node. Once you're on the Polaris login node, you can essentially basically forward that port again to your compute node. And that's done by this command here, which again just involves this L flag to specify you're looking for port forwarding, and then specifying the port and then the host name of your compute, the node where your compute job is running. So once those are all set up, you should be connected end to end. And then hopefully you should be able to navigate in a web browser on your local machine to localhost : whatever port you specified. Again, this is just a little warning that I already talked about, but you got to make sure that everybody who is doing this has a unique port, since only one gets assigned for all users or per request. So hopefully that everybody could have, who is interested is working through that and got that connected no problem. So the next part, I'll kind of talk at a bit of a high level about the concepts that we'll be looking at in the Jupyter Notebook, just to maybe introduce people who may not be familiar before diving into the actual code. So the first example is just a pretty straightforward example of trying to fit a straight line to some data points, and then using the idea being that by having a model that describes this linear relationship, you can then use it to predict some quantity of interest in the future. So the data we'll be looking at in this example is this real estate training data that's available from scikit-learn. The methods and the Python code for loading it and interacting with it a bit are shown there. And here's kind of what it looks like. So we have this data that basically describes the sale price of a home. And so this is a plot showing the sale price of a home versus the home square footage. And so our goal is to fit a straight line to this data point that allows us to predict, given the square foot of a home, we would like to be able to predict how much it will sell for example. And so we can do this using stochastic gradient descent as a method. And in order to do that, we need to have a criterion for evaluating our model's performance, right? So we need to be able to measure how well our model actually fits the data. This can be done by using what's called the mean squared error, which is essentially the sum squared differences between the model's prediction of the price and the actual true price. So the y hat through the next few slides corresponds to the true price of the house, and the y sub i's are the predictions from our model. Maybe some intuition for why we're choosing this model or how we're looking at it. So we want to express this relationship as just a slope times the area. And in this case, there's no y-intercept, because if the house has no square footage, then it shouldn't really sell for anything either, right? So that kind of makes a bit of sense why that's not there. The actual functions that we will use to do this are pretty simple and can be written pretty easily in Python. So first, we need a function that can predict the price given the current slope of our model and the area. And then we need a method for evaluating that prediction. So given the slope and the area, we can make a prediction of the price and then compare that to the true price. And this is the mean squared error from the previous slide. The details of the linear regression can be shown in more detail here, and the details for iteratively updating the slope of our model are kind of written out here in more detail for those who might be curious. Basic idea being that we start with some randomly initialized guess of our slope, and we can then update it successively using this update policy shown here. So basically, we start from a random number. We take a step of size alpha, which is the learning rate, in the direction of the gradient of our loss function. In our example, we're just looking at a simple mean squared error. So this gradient just follows through calculation, pretty straightforward calculation, and you end up with this expression here at the end. That can be implemented straightforwardly. I think I skip this. Again, in Python, using this this simple function learn. So given the input area and our current value of the slope and the true price and the learning rate, which defines the size of our updates, we first make a prediction given the input slope and the area. Using that, we can then calculate the gradient, which is that expression from the previous slide. And we can then update our slope given the current value, the learning rate, and the gradient. One thing to keep in mind or to kind of think about in all of this is the importance of the learning rate. And so in this stochastic gradient descent update method, we have this parameter, the learning rate, which essentially controls how large our step sizes are. And this can be problematic sometimes in the case where you have a value that is on either one of the extremes. So if you have too large of a value, it is possible that you end up just completely missing the minimum entirely and just bounce around. Conversely, if your learning rate is too small, it's possible that you might get stuck in some local minimum and never actually reach the global minimum. Or it's possible, you might just never get there at all. So if it's too small, you might even waste all of your computing time before you even get down there and never actually learn anything. So here's a plot from the prediction on that. So we can run the linear regression on that housing model and iteratively update our slope until we get some final value that seems to be stable and not changing. And using this model, then we can basically, it gives us a way to, for a new home, for example, we want to predict how much it's going to sell for. We now have a way to, predict that. Well, how well it actually does in practice is another matter, but at least it gives us a way to do it. The next kind of topic I'm going to talk a bit about briefly is the idea of data clustering. So this is probably somewhat straightforward to most of you. So at least this is something that you kind of have a physical, maybe intuition for. So if you have a bunch of data points, which should belong to set different distinct categories, for example, we would like to be able to find a way to effectively automate the clustering and identification of different points in that data set. So one thing that's always good to keep in mind is normalization. So it's always important to make sure your data is normalized. As you can see here, the original data here on the left, I don't know how well you guys can see this, the axes range from -5 to 10, -5 to 10, so these are kind of all spread out over the range of plus or minus 5 to 10. And after normalizing it, we can see that everything lies in this kind of 0 to 1 region and is a lot generally better and easier to deal with. And also is useful for these backpropagation algorithms and batch normalization and things. Having unnormalized data or data which may exist outside of bounds that you had anticipated can cause problems later on that are hard to identify. So it's just one of those things that's kind of good to keep in mind and in the back of your head. One of the probably easiest to understand and oldest algorithms for doing this clustering is what's called the k-means algorithm. And the goal of this is to partition some set of observations into a number of distinct clusters where each observation in our data set would then belong to the cluster with the nearest mean. So in this example, this is a pretty straightforward, simple example, but here on the left you can see we have some data points, and we begin by just basically randomly choosing 3 points anywhere in the data set. And we can then go through the process of iterating it. So step by step, what this means, starting from this initial data set, we randomly initialize 3 mean points, which are shown here in red, green, and blue. Following that, we calculate the distance for each point in our data set. We can then calculate the distance from it to each of the centroids. Once we have those distances all calculated, we can then, for each data point, identify which mean it is closest to. And using that gives us a way to kind of partition the data space. In two dimensions, it's pretty straightforward, and you can visualize it easily. But the same holds true in larger dimensions when you obviously can't just make a simple 2D plot of things. So having some kind of intuition for these types of things, I think is useful. Once we've identified which cluster each point in our data set belongs to, we then recalculate the centroid basically by looking at, it's essentially a center of mass calculation, right? Find the mean of all of our points and assign our centroids to these new locations. Once we've got these new means established, then the process repeats. And so we then calculate the distances again, identify which means each of our points are closest to, and split up the data again. And doing this procedure repeatedly will eventually reach some convergence where the locations of our means are no longer between successive iterations, the location of the mean doesn't change. and then you know it's converged, and that's about as well as you can do. So now I will, hopefully that kind of gave a bit of an intro, high-level overview of some of the stuff. Now we will go through the hands-on section and hopefully be able to run this notebook interactively. So just to make sure everything works, I guess I can go through it all right now too. So from the Polaris login node, we need to request an interactive job. So a single node for 1 hour on the debug queue should be fine. Once we're in our interactive job, first thing is to load this conda module. And then clone the GitHub repo. So hopefully this should all work live. I ran through it this morning without problems, so hopefully it doesn't give me any now. As long as, there we go. Also, obviously, feel free to interrupt me or ask questions at any point if anybody has anything. So once we've cloned the GitHub repo, then we can navigate into the statistical learning directory. And once we are in here, we then want to create a virtual environment. So this can be done by calling this VNV command and making sure we include the system site packages, which is important. And running slow for some reason. Nothing ever works when you try to do it live, right?
You go from Polaris to the final node, I get a password, but it doesn't work.
In the second step? Trying to, in the port forwarding, you say?
Yeah, the second localhost.
Yep.
You get a password, it locks.
Yep.
I thought I did something wrong. I went all the way back and tried it again.
Oh, okay. That's okay. Let's see. Yes. Okay. All right. Let's see. Let's see if it works for me. All right. So we've got this virtual environment created. We can then install the packages in here. What? So I forgot to activate the base environment, which is important and was giving me problems. So once we're in the base environment, remake the virtual environment. Once we're in the virtual environment, we can create an editable install. Okay. Yeah, it's interesting, right? Because I ran through it this morning. Yeah, source VNV activate. Installed it without a problem. Always good to have a backup just in case. All right. Well, so while I am trying to figure out why that doesn't seem to be working, we can go through the notebook anyway, so you guys can at least see the material and look at running it all. All right. That is a real confusing bug. Okay, all right, so anyway, it should still,
Go to the temp file and type the output. Should be a link in there. Bingo. Yeah, that's how you get it. So, you want to share that? But the question is,
now it seems to be working. That's strange. So picking back up where I left off, from within the virtual environment, you should hopefully be able to navigate within this statistical learning directory, and from, and Python pip install this project locally. To make sure that it was installed, you should be able to, the package is called ATPESC, so looks like that worked. You can see that it points to the directory that you're in. Once you've got that installed, the next step is to install a Jupyter kernel for the environment. That worked, okay, another good step. And then launch the notebook. I wonder if anybody took 8899, hopefully not. And then once you've launched the notebook, the next step involves connecting the port forwarding, as I explained earlier. So actually, this can be done from your local machines by specifying the ports to forward. First to the login node, followed by the compute node running the Jupyter notebook. So in this example, it's this host name here. Okay, so it seems like somebody is already on 8899. All right, that worked. All right, now we are connected to the Jupyter notebook on the Polaris compute node. From within your browser, again, going back to, just navigating to localhost, the port you specified, you should then get this Jupyter interface that allows you to then get to the notebook.
So I'm going to ask you for your password.
Yes. So that, so Jupyter has a method of authenticating users that functions kind of independently. It's just kind of its own independent authentication system. I don't know if it's necessary to set it up with a password. I think there are instances in which if you don't have it set up, then it tries to authenticate somehow and gets broken. And so I've ran into problems where people weren't able to connect, and then basically by setting a password, it allows you is a guaranteed authentication method. I don't know if it's necessary or turned on or not by default. It should hopefully just work without it.
Going to the local just blocked us, but then you have to go do it.
Okay. So yes, that's right. That's right. It's not an alternative instead of having to actually manually specify the token, which is yeah. So actually, thank you for that. That's a good point. And a very common problem that I've seen people trying to run into, or running into when they're trying to get things set up. All right. So now with all of that set up, hopefully this should work then without problems for the rest of it. So going through the notebook again, I'm not going to go and dive into the details of all of this since I kind of went over it already. But just for those who are curious, I can kind of run them all in order. So here we just kind of load this real estate data and look at it again like we saw in the plot before. You can see that the data is kind of roughly aligned along this straight line. We saw this previously again, so that's not important. Stochastic gradient descent. Oh, and so then this is the actual iterative part of this. So you can see here now that the slope gets updated each step. So each time we perform an update of our current slope, and then we can look at how it changes over time. So one thing that's kind of interesting about this is that you can see pretty quickly it, starting from whatever random point we started at, even though it was a very poor guess, it very quickly, within 10 steps, is more or less converged on a final value. The probably more interesting point of this talk involves this data clustering idea. And so, again, there's the normalization which we saw before, and the k-means clustering. So these are just, so the actual definitions of some of these functions are in here, so you guys can see them. The details aren't particularly exciting or anything, and are pretty much straightforward to implement. So there aren't any crazy tricks or anything to worry about, or trying to be clever or anything. And basically, just computing the distances from the centroids as you would expect. And then again, identifying the cluster for each one of our data points, as we saw before. I'll kind of go through this a bit quickly so we can get to the material at the end. Oh, I need to run these, otherwise I won't have the functions. And then we can actually look at running this on some real data. So we can, look at it and see. I don't know why it keeps scrolling down. That it basically, this doesn't do it. That's not a very great job, actually. Okay, so that seems a bit better. But eventually, this will basically just keep running until it reaches a point where either you've maxed out your iterations or the locations of our centroids stop moving. And in which case, then it has this little break statement. So it checks and sees if the locations of the centroids stop moving, and if so, then it breaks. And yeah, you can for this simple example, you can try playing around with different numbers of clusters and try to confuse. You can guess that an incorrect number and see how it does, things like that, if you really want to play around with it a bit more. This is actually a pretty important idea and a pretty important algorithm, and it seems straightforward and kind of obvious in 2 dimensions, but that is not necessarily the case when you have a higher dimensional data set with many different features. So this breast cancer data from scikit-learn has 30 feature columns, and so obviously is a much higher dimensional space, and it's not as straightforward to just look at 2-dimensional clusters. But we can do this same kind of analysis, running this k-means clustering on the data, and attempt to automatically identify our data points as being either benign or malignant, depending on their prognosis. So some of the additional details about the data set you can see here and look into with more detail if you were to want to. Basically, we extract the data extract the raw feature data into some vector x and the true labels of each of our data points. So the quantity of interest actually is whether or not the cancer sample was malignant or benign, and the goal is to run k-means to hopefully automatically identify that from the features present in the data set. So again, we normalize our data as I saw before. Another little point about the k-means clustering. So in this case, we were looking at a case where we want to split our data into 2 clusters, being either benign or malignant. And so we can look at how k-means does compared to the actual true label. And so you can see actually that it does relatively well. Obviously not perfect, but it's close enough that might be a starting point for more in-depth or informative analysis. Also, it kind of just goes to show the power of some of these ideas, especially on problems where your physical intuition isn't, as trustworthy. Another kind of thing to look at in these k-means plots or k-means analyses is this inertia quantity, which basically is a measure of how much work the model is doing in updating the locations of the clusters. So in this example, right? So if the data was clearly binary and it was very easy to split into 2 clusters, then we would imagine this inertia would drop off very significantly and then be more or less a step function. And so that's kind of a useful tool to give you some insight into how the algorithm's actually working on the data set that you're looking at. And so in this example, you can see it's kind of improving continuously. With each additional cluster, it kind of continues to try to improve. So like in this example, when we have 2 clusters, you can see that it falls off very quickly and doesn't get any additional information from trying more clusters, in essence. Probably one of the probably cooler parts of this talk, I think at least personally, is this idea of these self-organizing maps. So I won't have too much time to go into the details of this, but the idea it's kind of in the vein of this k-means algorithm, and the idea is that you map some high-dimensional vector space onto a smaller dimensional vector space, and then vectors that are close together in your original high-dimensional data space end up being close together in this reduced dimensionality. And by doing that, it allows you to kind of get this self-organization behavior. And this can be seen. So there's a pretty cool example we'll see here in a second that illustrates how this works. Again, I'm not going to have time to go too much into the details of this, but if you're interested, it's all here in the notebook and on the GitHub repo. But the basic idea being that you have some radius of influence that you are considering, and within that, you basically kind of follow an algorithm that's kind of similar to k-means, that again follows this iterative procedure. It's probably most illustrative if you see an example. So we can try to apply this idea to organize a two-dimensional image of randomly initialized colors. So you can see this example here, this is just a 50 by 50 image with pixels being randomly, the color of each pixel being just randomly chosen. And our goal is then to run this self-organizing map that will kind of organize all of the blues by each other, and so on and so on. And so we can then run it and see how it works. And so you can see really right away by the 50th iteration, it was already doing pretty good. And if you let it kind of keep running for a while, you'll continue to see this improvement where the map works to organize colors which are close to one another, and it kind of shuffles things around in such a way that all nearby colors should be hopefully roughly the same. And you can see it kind of moves around a bit as it updates. And so it kind of goes to show the power of this, these kind of ideas, and is a pretty, I think, at least illustrative example. It's you can see it actually working and get an idea of how it behaves, and see it update as it runs, which is nice too. So this should hopefully be done in a second. Yeah. Sure.
So how did you come up with the number of iterations?
So to be honest, it was as I was doing this and writing the material, I think I tried 1,000 first time, and I saw that it looked like it was still improving, so I just doubled it. It's not to get on too much of a tangent, hopefully, but that I think is part of actually what's a bigger problem in machine learning. This kind of idea of so people criticize it as being more of an art than a science sometimes, and I think some parts of that are true. And yeah, so I just did it by kind of trial and error, and that's I think how a lot of people actually fumble around on these types of things. For some certain problems, there might be heuristics or methods that you can follow that will lead you to good initialization of hyperparameters and things like that, for example. But unfortunately, there's not like a tried and true, this method will always work, which is a bit frustrating. And I wish I had a...
Like for k-means, there's elbow. Is there anything for?
So you can kind of do naive. I'm not sure if there might be a better method, but off the top of my head, naively, one way that you could do that in practice would be to kind of look at. You could kind of do it the same way, in a similar way to the k-means, right? I could find the average where my base red pixel is, and see how things change step by step. And so that's a good way. That's a good way of telling in general if between steps things are no longer changing. Then that's usually a pretty good indication that either your model is converged or everything is broken and it's all returning infinity every time or something. In which case you've got a lot bigger problems, I suppose. So we can, another kind of maybe useful visualization. We can look at how the map changes over at different iterations. So you can see here it starts from this random map of pixels. And already by 100 steps, it's doing pretty good. And from there, then it just pretty much tries to do its best at organizing things as well as possible. There are a lot of so I think the original example. So this is all material updated from last year, and I think the original example looked at like a 5 by 5 or 10 by 10 image, and it seemed like. It wasn't very illustrative. I think and so there's a lot of parameters you can try to play with in here and make it try to make it do better. You can change the image size, things like that. If you were to want to, it should all work. And all of the details for how to do that should be explained in the notebook, hopefully too. And then we can, at the end, look at our final self-organizing map and see how it did. Maybe last, I'll go through this a bit briefly, but the last thing really I wanted to talk about is that this idea of this self-organizing map, it's nice and kind of fun to look at the pictures like this, but the problem of arranging nearby colors by each other it's not very practical. I don't know. Maybe I'm not a graphic designer, so maybe this is more like other applications. But this general idea can be applied again to any sort of data set that you would like to have organized clusters in some way. And so again, going back to this breast cancer data set, again, we can apply it to that as well and see how the map learns to organize the points. Again, basically in this case again, now we have the binary classification problem, right, where we have either the tumors being malignant or benign. And so this cell basically runs an iterative self-organizing map again on this breast cancer data, and you can see how the how they change at each iteration. And again, look at the example at the end. And yeah, that's about it. So I know I kind of went through the Jupyter Notebook stuff maybe a bit fast because of the installation problems. But again, so all of this material is online, and it should be stable, non-changing. So if anybody has any questions about any of it, obviously feel free to ask now or whenever you get around to actually running it on the Slack workspace or whatever. But yeah, other than that, I guess that's about all I have for the plan material. If anybody has any questions or anything now, any problems that they were running into yet.
I just have a quick question about using unsupervised methods in science. In the example that we just saw, we knew that we had malignant and benign tumors. But very often in scientific applications, you have a bunch of data, you don't know what's inside. You do clustering, maybe 3 clusters, maybe 30, maybe 3,000, and you find these clusters and you're like, oh, okay, what does this tell me?
Yeah, so I was hoping nobody was going to ask that question. Yeah, right, because you're right, and that's a very good point and a problem. So I think that is a larger problem in this idea of scientific machine learning in general, because so they're kind of fundamentally disparate. They're kind of at the base level kind of in conflict a bit, because science is very much based on we like to think that it is rigorous and gets at some sort of ground truth about the world and is reproducible, and if I do my experiment now or 2 years from now, it should be the same. And that is, in my mind, very kind of in conflict with some of these ideas from machine learning, where even just the bare reproducibility problem is an issue, and all of these kind of things. People try to come to conclusions and interpretations about things that aren't necessarily logically consistent in times, and it's really so you're right. In this case, we're cheating because we knew the data ahead of time and we knew that it should cluster like that, but that's not always the case. And so that's why this is a good example to demonstrate that problem. But it's something that you really have to actually be thinking about and cognizant of when you're doing this, and especially when you're working on problems that have real-world applications. So my background is in high-energy particle physics, and I work on lattice QCD. So it's a bit more removed from every day-to-day life. But so for people who have like real impact and work with people and things that matter a lot more in the real world, have to think about it a bit more. And I would really emphasize be careful, because these things, who knows where they will be in 5 years. So it's, I think, important to get that at the ground level. Yeah.
Just tangent to that question.
Sure.
So do you think if we clean up the data, like for example using BCA, SVD, and then apply that to these methods, would that help?
So I think that's what it's done a lot of times in practice, especially when you have data that isn't and doesn't have any sort of categorical nature. So I think that is useful. So this idea of PCA is really, I saw a really neat visualization somewhere online once for anybody who might not be familiar, this idea of principal component analysis. So it's this idea of, so the graphic I saw one time this is still how I think about it in my head, is, if you have a shark that's trying to eat a big, a bunch of fish, right? And say the fish are aligned along some, straight line at an angle. PCA is basically the shark rotating along so that he can, swallow them all up in a single line. That probably wasn't a very good description, but I think that, honestly, every time I think about it, that's exactly what I come back to. And so this idea, that is useful for these clustering types of algorithms because in that case, your data then, you have whatever data you had originally, you can project it onto these principal components, which the first principal component is the axis along which your data varies most significantly. And so that at least has a consistent interpretation across whatever data set it may be. How useful that actually is in practice on your specific data set might vary a bit, but I think at least in that case that's useful because then at least everybody is talking about the same thing. Yeah, so yeah. Hopefully that wasn't too out of the blue. Yeah.
I'm curious in your interface currently if you have a GPU dashboard interface installed so you can see the activity utilization rate of GPUs while you say running some of those iterations.
So
speaking to that, can you go a little bit through how to guarantee that the APIs you're using are in fact using GPUs? I was curious that you use NumPy and not 2Py right now.
Yep. Yeah, absolutely. So we've actually internally been working on trying to identify and set up and build some of these machine learning operations tools. So things like monitoring, even experiment tracking, things like that. That's kind of something that we're actually in the process of trying to figure out how best to approach. So at the moment, there isn't anything like that to check, watch the GPU status. One tool I use personally in my research and experience is called Weights and Biases, so wndb.ai. And it's useful in that actually when you're running machine learning experiments, things like that, it actually will track GPU usage and stuff like that. But just for the sake of making sure that you are actually running on GPUs, one simple way is to import torch, PyTorch, and then check torch.cuda.is available. That's good. And so then you can also, there's a similar method in TensorFlow that you can do to use that, but at least that's right off the bat, easy way to check if the Python that you're currently in was built with GPU support and whether or not you can talk to them or not. Did that answer the question? Was there anything else that I missed?
Yeah, so I was just noticing you're using sometimes NumPy arrays instead of 2Py arrays, but there's Torch or whichever library you use do that for you.
Yeah. So for this, this example, since all of the none of it involves a neural network or any big training. It's all just written in NumPy at the moment, which obviously isn't ideal and doesn't take advantage of the GPUs. It doesn't matter so much in this case because all of the data is straightforward and none of it's really very compute heavy. But obviously that becomes a lot more important when you're running. So later in the day, you guys will see these data distributed deep learning examples, and in that case, it's much more important. And so, there are libraries like CuPy and things like that can automatically, go back and forth with NumPy arrays, which makes life easier. And there's, you'll see a lot of information about that today, later in the day as well. So I'm not going to go into too much detail. Any other questions? Yeah.
With that, no.
On Polaris, it is all, so on Polaris at the moment, I think it's all, since it's so new and so recently set up, it's kind of all in flux. I don't know if anything, so we actually also have a Jupyter Hub instance that is not set up on Polaris yet, which is why I didn't use it, but you can use it to log into Theta GPU or Theta, for example, using your crypto card password. And this can launch you right onto a Theta GPU node. Had this been available for Polaris, I would have used it. But I also think it's probably important to see this idea of port forwarding as well. Just because, so actually, it's a useful idea outside of just connecting to Jupyter notebooks. So if you, for example, wanted to run a TensorBoard server somewhere, you can use that same idea of port forwarding to connect your local machine to the computer that's running your TensorBoard instance, and then connect via web browser like that too. So it's just, I think something that I think is maybe useful to see or know. And so yeah, we're in the process of building out more of this infrastructure operations, like nice web-based interfaces that people can kind of click and automate things, make life easier for everybody.